Review for midterm number 2. B.1, quiz 2 questions, part 1, the first 3 questions. Question 1. Given an array with n elements, n greater than 2, if we know that there is at least one element that is not in place. All right? Yeah. Can we say that there must be another element that is also not in place? Okay. Before we look at this question first, so let's try to understand in place correctly, because you may get confused. Some students, point this out, what's the exact meaning? In place. We have 2 different meanings for this class regarding this in place. So you need to look at, so what are we talking about, right? What are we talking about? We're talking about in place elements or in place algorithm. Right? Yeah. Meaning is different. In place elements, that's the normal understanding. Yeah. All right. So the elements in right positions, in their right positions, right? When the array sorted, in their right positions. When the array is sorted. All right? Yeah. In-place algorithm. That's about storage space. Our main focus is on storage space used by this algorithm. So the extra space, because when you implement an algorithm, you need to use extra space. Is bounded by a constant. That's the second meaning. Yeah. But here, definitely, we are talking about the first meaning, in place elements. You can see one element that is not in place. So you can separate these 2 different meanings easily. Yeah. Look at the, the objects, the main objects that are modified by this in place, this phrase. Okay. All right. So here, so we can get to this question. It tells us there is at least one element in place. Can we say that there must be another element that is also not in place? Only 2 cases, true or false, right? Yes or no, only 2 cases. If no, so think about this. So here, you need to really get your logic straight. Not messed up, logic straight. Okay, in this way. Yeah. If no, so let's look at the consequence or the conclusion, the possible result we can get. If no, you cannot find another. That means there is only one element in this array that is not in place, right? Because you only find one, you cannot find the second one, right? You cannot find the second element that is not in place. So in this case, you get this situation. There is only one element in the array that is not in place. Right? Yep. So you have this situation. Now try to imagine, is that possible? The question, is this situation possible? Possible? Okay? Yeah. So try to go a few more steps further. Possible? If it is possible, so look at that. If possible, another assumption. If possible, what conclusion can we get? If possible, that means there are n minus 1 elements in this array. N minus 1, yeah, that are in place. Okay, the n minus 1 here, exact n minus 1. Exact n minus 1 elements in place. Then think about that. If n minus 1, if you know, in an n element array, okay, yeah, in an n element array, so n, total number, but you know there are n element, n minus 1, already in place. In place. How about the last one? The last element that is supposed to not in place, but it has no choice. Only one position left. That element can only take that one position, but that position is also in place. Right? That position is also in place. The last one, even the last one must be in place. So that means you cannot get this situation. There are exact n minus 1 elements in place. You cannot get that. You can never get that situation. So that means these, if no, all wrong. Because you get some contradiction. You get some contradiction, right? So if when you assume it is no, you get contradiction. Answer is yes. The answer can only be yes. So you can see, in order to get a correct answer, you need to do a lot of analysis here. A lot of analysis here, okay? Yeah. Some assumptions, some deductions, some conclusions, and finally some contradiction. After you go through all these steps, logical reasoning, you can get a correct answer. All right, so next question. When we apply the selection sort on an array with n elements, n greater than 2, let us denote B of n best case efficiency, number of comparisons for the best case. Okay? W of n number of comparisons for the worst case. We usually have, the conclusion statement. We usually have that W of n greater than B of n. But here we are talking about selection sort. All right. So you need to be familiar with the selection sort first. If some students, so they did not study the selection sort, they just use their, intuition, basic understanding, real life experience, then it is very likely they will choose true. They will choose true. So why? Because in our real world experience, usually the worst case number should be greater or equal to best case number, but it is more likely greater than best case number, right? Yeah. So that's based on the real world experience. But here, it's not that case. Here, you need to get to the details of the selection sort. It's different. Selection sort is special. Regarding this part, it is special. Okay? So actually here we can talk about bubble sort together because regarding to this part, they are the same. So even the bubble sort. Okay? So in this part, they are the same. Yeah. And I can also use A of n regarding the average case. Okay, so three functions, B of n, A of n, W of n, for selection sort, bubble sort, they are all equal. So let me write this way. Selection sort, bubble sort, they share the same property. B of n equals A of n equals W of n. Because when you implement the algorithm, you have only one choice to do. From beginning to end, you do not have other options. You only have one way to go. No option. No other options. Only one option. So that's why for one option case, all these numbers are the same. Yeah. So the answer false. Yeah. All right. Next. Question number 3. When we talk about the input size of a computing problem, we always mean the number of data items in the given input. Number of data items. Most of the time, but not always. Okay? So not always. Most of the time, because there is another case that happens less frequently, but it happens. Okay? Another case is the input size could be magnitude. Magnitude of the number. Okay? So for example, for n, magnitude, the value of this n. Magnitude, the value of this n. Okay? So for example, in this class, we have two examples. Okay? The first one, prime factorization, given a number, you need to factorize all of its prime factors. That computation, you need to use magnitude as its input size. Only one number. You do prime factorization on one number. One, the number of data item is one, but its magnitude cause the problem to be harder when the size is large. That's the first one. The second one, greatest common divisor. Okay? In these two cases, we use the magnitude meaning, not the number of items in the input. Yeah. All right. So that is our part 1 of quiz 2. So let me stop here. Yeah.